Welcome to the course on biostatistics and design of experiments. We have been talking about various types of designs, okay, screening designs, various types of screening designs. Okay. One of them, the most important one, is your factorial design. Then we looked at the fractional factorial design, that means doing a fraction of those factorials. Then I talked about something called the confounding. Then I also talked about the resolution. Okay. So resolution 3 designs are not generally liked, resolution 4 or above are already liked, and if you say 2 power 4 minus 1, that means 4 is the number of factors or parameters you are looking at, and this is a half of that. So 2 power 4 is 2 into 2 into 2 into 2 is 16, half of that will be 8 experiments. So what do you do? 8 experiments is so you put the new variable d, new factor d in place of ABC. So you have a confounding of d and ABC. Okay. This is a resolution 4 design because there are 4 terms and the design generator I is equal to ABCD, understand. So that is how you go about doing that. So resolution 4 design, this is light. Okay. Resolution 3 design is not light. So what do you do? 3 parameters or 3 factors. So 2 raised to the power 3, 8 experiments, you do not want to do 8 experiments. So what do you do? 2 raised to the power 3 minus 1. So it is half of 8 experiments, you are doing only 4 experiments. So what do? You replace AB with C, that means AB is confounded with C. So the design generator is ABC, I is equal to ABC, and this is a resolution 3 because you have 3 parameters and so on. So you can this tells you the which terms are confounded, okay, and then it also tells you, allows you to make your resolution. Okay, this will be a 4 resolution and so on, number of runs. So and I also taught you how to do the calculations later once you have the results also. Okay. Now then we went into something else, the Plackett-Berman designs. These are also very good screening design. We can screen large number of factors in very minimal experiments. Ideally if the factors are like 3, 7 and 11 and so on, because the design generator for Plackett-Berman designs are meant for 8 runs, 12 runs, 16 runs, 20 runs, 24. So if we have one factor less than that, then Plackett-Berman design is very good, because with less number of experiments you can get very good idea about the main effect. So you have the design generator here. I taught you how to build up these tables. Okay, the last row generally, last row is always minus minus minus, and you push these signs up and build up this. So Plackett-Berman design is very good if you have parameters, okay, like 3, 7, 11, 15 and so on. If the number of parameters is not that, slightly less, we can always call some of them as dummy variables. Okay. Some of these columns can be called dummy variables. Okay. This is taken from this particular reference. Then we talked about Latin square design. This is also very important, useful type of design. Then I showed you a Latin square for 3 parameters A, B, C, each operated at 3 levels. So how do you represent that? Minus 1, 0 and 1. In a 2 level we say minus 1 and 1, for a 3 parameter we say minus 1, 0, 1. Okay. And here you can see you need to do 9 experiments. So this will be 1 experiment, this will be 1 second experiment, this will be third experiment, 4, 5, 6, 7, 8, 9. So it is very nice Latin square designs for a 3 variable problem. Okay. If it is a 2 variable problem, we can have a 2 by 2 Latin square. Okay. We do not have to 2 variable problem, we can go even 2 levels, 2 variable, we can have 2 by 2 Latin squares and so on actually. Then comes another design, this is also a screening design, that is called Taguchi designs. Traditional DOEs focus on how each level or each factor, sorry, not each level, each factor affect the output, that is y. Y is your output or the dependent variable. Suppose I am doing a bioprocess like yield of a metabolite or biomass, that is the output. Whereas in Taguchi design he has looked at robust design and he is more interested in the variation, okay, the loss function. So, he is looking at Taguchi that has developed designs looking at them as a possible robust designs and also looking at the variations, okay, rather than the averages, whereas normal designs like your factorial designs or even your Plackett-Berman, we are looking at average output, we are more interested in that actually. So, Taguchi design, you go, there is a design selector is there, okay. This tells you number of parameters, this tells you number of levels, this table was taken from this particular reference, okay. So, this tells you the number of levels, this tells you the number of parameters. So, if I have a 2 by 2, that means 2 levels, 2 parameters, there is something called L4 design. If I have that table L4 is available here, okay, table L4 is available here, okay, this is called a table L4. So, we can pick up the as you can see L4 and 4 rands, okay, we can pick up this. So, we can pick up column 1 and 2 for A and suppose I have 2 variables. So, I can do these 2. Okay. If I have 3 parameters also I can take up this. So, this will become like a confounding, okay. Do you understand? And so on. So, if you look at this table, there are tables available like L9 table, L18 table, L27 table, they are meant for 3 levels and so on. L16 tables meant for 4 levels, L25 tables, 50 tables available for 5 levels. So, standard tables are available, we just pick up and then use it. So, let us look at this level 2. So, you have tables for L4, L8. So, we can do it for, suppose I have parameters 3 or 2, I can use the L4 table. If I have parameters 4 or 5 or 6 or even 7, I can use the L8 table, okay. And if I have parameters 8, 9, 10, 11, I can use the L12 table and so on actually. Okay, so, if you look at the L4 table, 2 levels, I can do a full factorial design, I can if I maintain 2 factors I can get a resolution 4, or I can go up to 3 factors for screening. So, if I am interested in doing a screening type of work, I can go up to take this table and I can look at 3 variables. For example, this is the L4 table, 4 rands, this is for factor A, factor B, factor C. So, if I put A, B, C, then obviously it becomes a screening design, whereas if I put only A, B, I can do a very good high resolution full factor, it becomes a full factorial design. Okay, this is the table called L4 table. So, I just blindly do this, pick up the L4 design, okay, for 2 levels, and if it is 2 factors I put A, B, ignore this, if it is 3 factors I put A, B, C and do the experiments accordingly. Okay, let us look at L8 design, that means 8 rands, this number tells you how many rands, 4, 8, 9 and so on. So, the 8 tells you number of experiments. So, if you look at L8 design, 2 levels, if I have 3 factors it becomes full factorial, right, 2 raised to the power 3 is also full factorial, okay. But if I want to do a screening I can go up to 7, it is almost like your Plackett-Berman, okay. If I want to get resolution 5 then I stick to only 3 factors. So, let us look at L8 design, this is how it looks like. So, either I can have a less number of factors, okay, I can have only 3 factors, then it becomes full factorial design, that means A, B, C. So, this will become A, B, this will become B, C, this will become A, C, this will become A, B, C, okay. Or I can have 7 factors A, B, C, D, E, F. I am doing 8 experiments, it is like your Plackett-Berman design. Notice that even here you will have the balancing 4 minus is 4 plus. So, you should always have a balance and orthogonal type of behavior. So, if I want to do a full factorial design, so I can select this, I can select this. As I said, 2 raised to the power 3 is 8 experiments. So, I can select this, I can select this, okay. Then I do not select this of course, because this and this looks same. So, I will select this, do you understand? That is why I select this column and this column. So, if it is a 3 factor full factorial design. So, if I want to do screening up to 7, then I can go right up to 7. I can have A, B, C, D, E, F like that, no, completely. So, I can keep increasing. So, 1, 2, 4, 7, okay. So, I will not use 5 because 4 and 5 look similar. So, I can use this, I can use this, I can use this, okay. Then I can use this. So, like that because some of 4 and 5 like that, no, they are all similar. So, L4, L8. So, we can, if I want to do a full factorial design, I select I can do up to 3 factors. So, that will become a full factorial design with their interactions, and then if I want to look at 7 factors also I can go, it will be almost like a placket. Then you have the L9 designs. L9 designs are generally for 3 levels, -1, 0, 1, okay. If I have only 2 factors, so it is 3 power 2, which is 3 into 3 is 9. So, full factorial I will get, but I can go up to 4 factors as a screening design, okay. So, I can go up to 4 factors, so 9 rands. So, as you can see, minuses, zeros, 1. So, this is at the highest level, these are the lowest level, this is at the middle level. For example, temperature, if I am interested in looking at 30, 40, 50, plus 1 means 50, minus 1 means 30, 0 means 40. pH, if it is 3, 4, 5 I am looking at, so minus 1 means 3, 5 is plus 1, 0 is 4, like that, you know. So, if I want to do a full factorial design, what I do is I will take 3 factors I can do, okay, column 1, column 2 and column 4, okay. Or screening design, like that you can keep on doing it, you can add many factors actually. Then you also have these L12 design. So, as you can see here, L12 design 2 levels. So, we can use it as a screening design for 11 factors. So, I can put 11 factors here, A, B, C, D, E, like that. So, I will do 12 rands. This is almost like your Plackett-Berman design, okay. It is like Plackett-Berman design, okay. Only thing is the columns and the rows have been permitted. So, they have interchanged the columns and the rows actually in some cases, whereas in Plackett-Berman design, if you see at the bottom you will get always negatives, right. So, some difference is there. So, last line will always 12 rands will always get a negative. So, there is a switching over of some rows and columns, but it is exactly like Plackett-Berman. So, 11 factors I can use a Plackett-Berman design and do 12 experiments, or I can pick up this Taguchi table for L12, I have 11 factors and I can do a screening design, okay. So, I have both the options actually, I can take Taguchi or I can take Plackett-Berman for 12 experiments. Then you have a L, so just like L4, L8, L9, L12, you also have L16 table, okay, this is L16 table, okay. So, there are 16 runs. So, this indicates the number of runs, you have 16 runs here, okay. So, I can do a full factorial, 2 raised to the power is a full factorial, right, 2 into 2 into 2 into 2 4 times. So, full factorial, okay, full factorial will give you full factorial of 4, I can go up to 5 factorial and maintain resolution 5, okay. If I want to do a screening design, I can go up to 15, just like your Plackett-Berman experiment, right, 15. And then there are L18 designs, that means 18 experiments, 27 experiments and so on actually. So, the advantage of the Taguchi designs are there are tables available, okay. We can use different tables for different, if you have the depending upon the number of parameters and number of levels you have, okay. If the parameters are less in that what is available in the table, we can ignore that, okay. Then one important point is you need to cross check whether there is a balance and orthogonality taking place, because any design you take you need to have that sort of condition, that is very important, okay. So, sometimes it will look like even Plackett-Berman design, especially when you are looking at L12 and go screening for 11 factors, okay. Then of course, it is like a Plackett-Berman design. So, we have different types of tables, that is the advantage of this type of Taguchi method. This is an L18 design, we have 18 experiments here, okay. This is at 3 levels, we have -1, 0 and +1, 3 levels, okay. So, the main advantage as I said is there are designs tables available, Taguchi has prepared and given it. So, we can use those tables directly, and whether it is a 2 levels or it is a 3 level, there are tables available. Even see, as you can see here, 2 levels, 3 levels, 4 levels, 5 levels, there are table levels. Generally we will not go 4 levels and 5 levels. So, 2 levels, 3 levels, there are table available depending upon the number of parameters. There are tables for L32 also, that means 32 experiments you need to do. So, you just pick up those tables and make use of for your design. So, we have covered a lot of designs which can be used for screening, the full factorial, the fractional factorial, the Plackett-Berman design, the Latin square design, the Taguchi design. So, all these are very good. Taguchi of course, you can mix and match and use it for full factorial or even fractional factorial. Okay, all these designs are at 2 levels, that means you can get a linear relationship between if temperature varies from 30 and 40, 30 to 40, I am measuring at 30, I am measuring at 40. pH I am measuring at say 3 and measuring at 4, okay, the effect of pH. Carbon concentration measuring at 1% and measuring at 2%. So, I am measuring at 2 places, obviously I can get linear relationship. So, if I am generating regression equation, I can get a linear relation. Okay, if I want to get non-linear relation, ultimately we are interested in optimization. So, in such situations I need to have data at more than 2 points, then only I can get at least a square term, then only I can get a quadratic term which is non-linear, then I can find an optimum maximum yield or minimum impurity and so on actually, okay. In a linear it is always increasing or always decreasing, monotonically increasing or monotonically decreasing, there is no optimum. So, initially during screening design we do all the experiments at 2 levels, okay, whether it is 2 raised to the power n or 2 raised to the power n minus 1 or whatever it is, okay. So, we will have -1 plus 1 as your coded experimental strategy, okay. We cannot use the results we get to develop a second order type of model, we can use it to develop a linear model, not a quadratic model. So, screening designs are used for eliminating many parameters which are of no significance, okay, and screening designs can be used to develop a linear relationship. But if we are interested in developing non-linear relationship, then we need to go for second order model. So, when you start your design you do not immediately jump into second order model, that is a very bad idea, okay. What you do is you do a screening design, you have 5 parameters, you do a screening design, come down to 2 parameters and then you do a second order design for those 2 parameters, okay. Because when you are doing second order design you may require the results at 3 levels -1, 0, 1. So, the number of experiments also increases, because if you have experiments at 3 levels you will be able to get a quadratic relationship, okay. So, always remember when you start your design experiments never go for second order model, second order designs. Start with screening designs like fractional factorial or Taguchi method or Plackett-Berman or even Latin square, eliminate many variables and then do a detailed design, and that is what we are going to talk about. These detailed designs are generally second order designs which can be used to generate nonlinear relation like a quadratic relation. Okay. So, these second order designs are extremely useful. In the later part we can use those designs for optimization. I want to calculate maximize my biomass production, I want to calculate maximize my metabolite production, then we need to have a second order model or a quadratic model. So, there are some designs in second order also. One is called the central composite design, 3K factorial design, box Benham design. So, these are some designs. Many softwares, commercial softwares automatically will give these information. Okay. So, it is not a big deal, and I will also tell you how to go about doing that, and it is very useful to do that even using a paper and a pencil. There are other designs, Koshal design, hybrid design, we will not talk about it. The main designs I will talk about is the central composite and box Benham design. These designs are very useful and well used generally and well accepted. Okay. So, the second order designs, of course, you have to have the data at 3 levels of the factors -1, 0, 1. That means temperature at 30 degrees, 40 degrees, 50 degrees. Whereas, when you are doing a screening design, if you are changing temperature, you may do at 30 degrees and 40 degrees or 30 degrees and 50 degrees only. Whereas, if you are doing a second order design, you will have at 3 levels. So, you will do a 30, 40, 50. Of course, you may ask the question, can I do a 3 power n raised factorial design also? Yes, you can do that, but you do not do 3 power n designs during screening process. Okay. Never do that actually, because the number of experiments increases, you do not know which factors which are of no use. So, during after screening you may eliminate some factors, then what is the point in doing too many levels of unwanted factors. That is why screenings we generally do it at 2 levels, and later on detailed design we can do at -1, 0, 1. Okay. So, central composite designs okay, developed by Box and Wilson. Okay. These are first order designs, okay, with augmented with center points and star point. Okay. So, center point is right in the middle and star points are outside this first order designs. First order designs are your factorial designs. 3K factorial design, fractional arrangement with K factors each at 3 levels. Box Benham design, this is also almost like central composite, but the corner points are not used, so they use some other points. Okay. So, we will look at each one of them. Okay. So, imagine I have a factorial 2 power 3 8 experiments, right. 1, 2, 3, 4, 5, 6, 7 and inside 8. So, for a 2 power 3 it is like a cube, the pyramid factor A, factor B, factor C, each one at -1 and +1 level. Okay. Factor A, factor B, factor C, each one at -1 and +1 level. So, it is 2 power 3. So, it is like a cube. In a central composite design, so in addition to these 8 places full factorial, we do experiments at the center point here, and we also do experiments at 6 star points which are outside this cube. Okay. Do you understand? So, 8 experiments plus 1, 9 experiment and 6 star points. These are, there are 6 faces to the cube. So, there will be 6 star places which are outside the face, that means outside, that means it is beyond the +1 level or below the -1 level, they are called the star point. So, totally for 3 factors you do 8 plus 1 9 plus 6 15 experiments, you will get, you are actually doing experiments at 5 levels. Can you imagine? The one below the -1 level is 1 level, the -1 is 1 level, the center point is 1 level 3, and then again +1 is 1 level, and above the +1 another star is another level. So 5 levels, 1 2 3 4 5. So each of these 3 variables you are doing at 5 levels. Fantastic, isn't it? At 5 levels, but you are doing only 15 experiments. So we can fit nonlinear equations for effect of factor A on your the output, effect of factor B on your output, effect of factor C on your output, just by doing only 15 experiments. That is the beauty of the CCDs. So we cut down number of experiments tremendously, but we get a lot of information using this type of approach actually. Okay? That is the main advantage. Now how do you decide on the star points? These star points are outside the cube, outside the phase of the cube. So you will have 6 phases for the cube. So obviously there are 6 star points. Do you understand? So there are 8 for the factorial, there is 1 central point, 9, 6 stars, that is above +1, below -1, above +1, below -1, above +1, below -1. So there are 6 experiments. So 8 plus 1 plus 6, 15 points each. That means you are doing each variable at 5 levels. So you get very good idea about the effect of each parameter or factor on your output, and you can develop very good nonlinear relationship. It is even better than your 3 raised to the power n design, because in 3 raised to the power n you are doing only at 3 levels, but the number of experiments may be very high. Imagine if I want to do a 3 factor ABC at 3 levels, a factorial, it becomes 3 raised to the power 3, which is 3 into 3 into 3, that is 27 experiments, whereas with 15 experiments with CCD I can get lot of information also. That is the main advantage of the CCD. Okay. So the I do the full factorial inside, that means I can get some quite a lot of idea about my interactions also. Then I do these extra star points and central points. So I am doing each variable at 5 levels also. So it is much superior to 3 raised to the power 3 type of designs. Do you understand? So it is really good. The other one is the box Benham design. So instead of doing at these corners, it does it at these center places of these edges, center of the edge, you know. So this is what this picture is about actually. So you do the same thing, you do at the center of this cube, but you also do experiments at the center of these edges rather than corner of these cube. Okay. Of course, if the factors are 3 to 7, only it exists. So it is not the corners it is doing at these edges, center of these edges actually. That is called the box Benham design. Okay, so if you have say 2 parameter, that is like your square, okay, that is like your square, and if you are doing a CCD, the 4 points in the square, that is the 2 power raised to the power 2, the center point, and if the star point is at the edges, so these are the 4, okay, these are called the star points. So when you are doing high, medium, low, okay, medium is your 0 0, so this is the design. But if you can extend this little bit, okay, if the region of interest is more, so that way you, if I little bit you are ending up doing 5 level type of experiments, whereas if you are keeping your star points right on the edges, you are doing only 3 level experiments for each of these parameter or variable or factor, it will be high, medium, low only. Okay. So, if you extend it beyond, then you are doing it at 5 level, do not forget that, see this is what it is. So, if you are extending it beyond, okay, those points, so you are doing at 5 levels. Each variable is changed from, this is level 1, level 2, level 3, level 4, level 5. So, each variable is changed. So, here we can say the star point, if we call it alpha, if alpha is 1, those points lie right on this, whereas if alpha is greater than 1, they are beyond the square. Okay. So, we are exploring beyond the square, that is what it is all about actually here in this type of design. And this is for a 2 raised to the power 2, that means if you have 2 parameters. Okay. How do you calculate this, what is the optimum distance for this? Okay. Generally the formula is square root of 2 is the optimum distance. So, if this is 1, okay, then this will be 1.414, because square root of 2 is 1.414. Okay. That is how you select, and then you go beyond that actually. Okay. That is how you select, and so we have 15 points, sorry, if we have a 2 raised to the power 2, okay, we have 4 points here, central point is 5, and then we have another 4 points. So, that means you have how many experiments? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9 experiments. Okay, for a 2 by 2 at 3 level, okay, it is 9 experiments. So, if you have a 2 parameter, if I am doing a factorial 3 level, I can do 3 raised to the power 2, which is 9 experiments, but you are doing only at 3 levels. Okay, whereas here we are doing, when I use a CCD, central composite design, I am looking at each variable at 5 levels, 1 level, 2 level, 3 level, 4 level, sorry 3 level, 4 level, 5 level. Okay, each variable is being looked at 5 level. So, CCD for 2 factor, the number of experiments is same as the number of experiments for a factorial design of 3 raised to the power 2, but each variable in CCD you are looking at 5 levels, whereas each variable in full factorial 3 raised to the power 2 you are looking at only 2 levels, sorry 3 levels. So, that is the difference. So, CCD will be much better than your 3 raised to the power 2 type of designs. Okay. So, we will continue more about these second order designs in the next class. Thank you very much.